So, properties of matter. Matter is anything that has mass and takes up space or has volume. In class today, we were talking about the difference between mass and weight because these are two words that are commonly used interchangeably, but they do not mean the same thing. An object's mass is the amount of matter, so measure the amount of matter that the object has. Your mass will remain constant at a given point in time. It remains constant with gravity. In other words, if we were to leave today here from Cape Fear High School and all get on a space shuttle and travel to the moon, our mass would be exactly the same on the moon as it is here on Earth, unless you lost part of your body along the way. And we would definitely try not to do that, but your mass is how much matter you possess. Now, your weight, on the other hand, weight is a measure of Earth's gravitational pull on your matter. So, since the gravity is different on Earth than it is on the moon, you would weigh less on the moon. In fact, oftentimes you're described as being weightless on the moon. In reality, your weight would be 1/6 what it is here on Earth. So your weight depends on location. It will change because it changes when gravity changes. Think about this. I want you to pause the video and try to answer these two questions, and then check and see if you got them correct. Where would your mass be greater, on the Earth or on the moon? Well, we just said that mass is constant, regardless of your location. So the answer here would be they're the same. Your mass would be the same in both places, on the moon and on the Earth. Now, where would your weight be greatest? Well, that would be on the Earth because Earth has a greater gravity. So you're going to weigh on Earth more because the gravity is more on Earth. This leads us to a very important law that we need to be familiar with. It's called the law of conservation of mass, also known as the law of conservation of matter. We will abbreviate this LOCOM for law of conservation of mass. This law states that mass cannot be created nor destroyed in a normal chemical reaction, and RxN is how I abbreviate reactions. So if you take this generic chemical reaction, let me just remind you, in this example, A plus B would be referred to as the reactants. And then C and D, whatever they might be, are considered the products, what you produced. And this is our yield sign. And with this particular concept, you want to treat this like an equal sign. So mass is conserved, and what that means is the total mass of your reactants must equal the total mass of your products because it's conserved. Again, you treat your yield sign as an equal sign. So if you know that you start with 12 grams of A and 8 grams of B, that is equal to a total of 20 grams. So on this side, you would have also produced 20 grams according to the law. So if you were asked to figure out how much C was produced, how much of substance C, and you knew that 5 grams of D were produced, then you just do a little simple algebra here. What plus 5 is equal to 20? Well, the answer would be 15. So your answer would be 15 grams. Again, locate your yield sign and treat that as an equal sign. On to the states of matter. Matter is actually, there are 4 states of matter. Now, oftentimes we think of just the solid, the liquid, and the gas state because we encounter those daily. But the 4th state of matter is the plasma state. You find the plasma state like on the surface of the sun and in the stars and in lightning. So that is the 4th state of matter. Let's talk about some characteristics, though, of the 3 most common states of matter. solids, liquids, and gases. During this part of the video, if you need to pause it to copy the notes down, please pause the video. I'm going to go through the slides pretty quickly, but of course, as I said, you can pause it if you need to stop it to copy these. Solids have a definite shape and a definite volume. The particles of a solid are packed closely together. They have an orderly arrangement. And we say solids are almost incompressible. Of course, with enough pressure, you could crush or crumble the solid, but under normal pressure, solids are considered incompressible. Here is a picture of an example of a sodium chloride crystal. Notice the particles are thought of as small hard spheres, and they're packed tightly together with a very definite shape, and you can determine the volume by taking the length, width, and height of this cube. Some examples of substances that would be solids at room temperature are bones, coal, sugar, ice, and iron, the element iron, a metal. The liquids. Liquids have a definite volume. You can measure the volume of a liquid. So from here, they're pouring a liquid out of this Erlenmeyer flask into the beaker. So let's say, for example, if there were in the Erlenmeyer flask, if there were 20 milliliters in the Erlenmeyer flask, and they were to pour all of that into the beaker, there would still be 20 milliliters. The volume is the same, a definite volume. They have no definite shape, however. They take the shape of their container. Here you see that it is being poured, so they flow freely, or they are what we call fluid. They flow. And liquids, just like solids, are almost incompressible. Now, I will demonstrate this for you in class because this is something that students oftentimes misunderstand. But liquids are incompressible because the particles are all touching one another. You can't push them any closer together. Water is a liquid, milk is a liquid, and so is blood at room temperature. The third state of matter is your gas state. Now here in this box, you see the particles are represented in this box as the gases are spread out. So gases do not have a definite shape or a volume. The particles spread out and they're able to flow. So they're also fluid, just like a liquid. They're easily compressible because their particles are so far apart. Here you see in this this picture here, this representation, there's space between these gas particles, so theoretically you could push them all together until they all touch. So that's what we mean by compressible. I will demonstrate this in class as well. Now pause the video for just a moment and you try to classify these as to whether they would be solids, liquids, gases, or plasma at room temperature. And if you ever see the abbreviation STP, that means standard temperature and pressure, then that would be sort of the same kind of question. Room temperature sometimes is referred to as standard temperature and pressure. Pause the video, answer these, and then resume and check your answers. Gold, of course, is an element from the periodic table. It's a metal, so it's a solid at room temperature. Gasoline, when you pump gas into your car, we all know that's a liquid. Hopefully you got that one right. It's a liquid. Helium is another element, but it is a gas. You think about putting helium in a balloon. Helium is in the gas state at room temperature. And diamond is also an element. It is pure carbon. It's one of the forms of carbon. There are 3 forms of carbon. Diamond is one of them. And diamond is, of course, a solid. If you have a diamond ring, diamond is a solid at room temperature. Also, if you're writing with a pencil, we call it pencil lead, but it's really carbon. It's graphite in your pencil. All right, that's our lesson for today. I'm going to put another link up for you to look at an animation.